Okay, ladies and gentlemen, we are going to venture into our next chapter. We're going to move beyond sampling distributions and we're going to look at how we can estimate population parameters with a certain amount of confidence. So we're going to introduce the concept of confidence intervals today, and we'll finish that up in the next video and then get into how we can use these skills to estimate population proportions and then population means, using many of the same skills that we saw in the previous unit on sampling distributions. So here we are. Here are the learning objectives for section 8.1. We will be looking at what confidence levels and confidence intervals really are. What does it mean? How can we interpret them? And how do we find them? So our goal with statistics oftentimes is to use a sample statistic to estimate the population's parameter. In chapter 4, when we were looking at how to design experiments, we needed to randomly select the sample. And by doing that, we were able to avoid bias and generalize our results to the population of interest. In the previous chapter, right before this, we looked at sampling distributions and we talked about how different samples yield different results for our estimates. Statistical inference uses the language of probability to express the strength of our conclusions. And what we're doing is we're taking chance variation due to random selection into account. So we're taking these two ideas and we're pulling them together, and we're learning how to make statistical inferences using these things called confidence intervals. What we're going to be doing is we're going to be estimating the parameter from the statistic. We'll look at how to construct confidence intervals and what would happen if we use the inference method many times. So, to introduce this concept, I've selected a mystery value that will act as a mean value. That's our population parameter. Our task is to estimate that value. And using a calculator, I can take a simple random sample of 16 observations from a normal population, that's rand norm, with a mean of m, that's my parameter, sample size, standard deviation of 20, sample size of 16. And the average of those 16 things, the mean value is 240.79. So this is my x bar. My standard deviation is 20 for the population, and my sample size is 16. So our task here is to determine an interval of reasonable values for the population mean mu. We want to look at the result right above this and look at what we learned about sampling distributions to come up with this interval. So I'm going to suggest that you pause the video and think about what we could do to come up with this interval before you go any further. So, before we answer that question, before we get our interval, if we had to give just one number to estimate our parameter, what would it be? Well, if we're estimating the mean mu, you would probably use x bar. If you're estimating a population proportion p, we'd use p hat. In both cases, what we're providing is a point estimator. That point estimator is a statistic that provides an estimate of the population parameter. The value of that statistic from a sample is called the point estimate. In the previous here, our point estimate is 240.79. Ideally, a point estimate is our best guess at the value of an unknown parameter. From the previous section on sampling distributions, we know that the ideal point estimator will have no bias and a low variability. Variability will always be present, and we need to take our thinking about these estimates and acknowledge the fact that repeated sampling could yield different results. Every sample that we take, if I were to run that calculator command multiple times, I would get many different point estimates. And because of that, we need to develop a method for accounting for that variability. So let's go back to this activity. Is the value of the population mean mu exactly 240.79? It might be, but it probably isn't. But we know that the sample mean is 240.79. We could guess that mu is close to that. But how close is mu likely to be? That's a good question. And to answer that question, we have to ask, how would the sample mean x bar vary if we took many simple random samples of size 16 from our population? Let's look at the shape. Population is normal, so the sampling distribution of x bar is normal. The center, the mean of the sampling distribution of x bar, will be the same as the mean of the population distribution mu. And our spread, the standard deviation of x bar for an SRS of 16 observations, is found right here, standard deviation of the means. These are skills we saw in the sampling distributions chapter. And we get this sort of picture going on. We have our population with some mu and a standard deviation of 20. We sample a bunch of times, get a bunch of different means, and we create this population, or the sampling distribution. And we don't know mu, but we know that the standard deviation of the means is 5. To estimate the mystery mean, we can use x bar from our calculator sample as a point estimate. We don't need to expect mu to be exactly x bar, but we need to think about how accurate our estimate is. In repeated samples, the value of x bar will be normal with a mean and a standard deviation of 5, which means the empirical rule tells us that in 95% of all samples of size 16, x bar will be within 10 units of mu. That's 2 standard deviations. So this right here, this is very powerful. And this we're going to rely on quite heavily as we go through these confidence intervals. Here's another jump that we need to take. If x bar is within 10 points of mu, we can turn that around and say that mu is within 10 points of x bar. That should make sense to us. So therefore, the interval from x bar minus 10 to x bar plus 10 will capture or will contain mu in about 95% of all samples of size 16. And this, ladies and gentlemen, is a confidence interval. If we use these 10 points within x bar, we are estimating that mu lies somewhere in the interval 230.79 to 250.79. What we're saying is that this interval will contain the true value of mu in about 95% of all possible samples of this size. Okay, so big idea. The sampling distribution of x bar tells us how close to mu the sample mean will be. All confidence intervals we construct will have a form that looks like estimate plus or minus margin of error. And here's the definition of each of these things. And I want to talk about this down here. The confidence level, C, is a percentage. The confidence level in the previous problem was 95%. That is, in 95% of all possible samples, that method would yield an interval that captures the true mean parameter value. That wording is going to be very familiar to us. And we always want to choose a confidence level of 90% or higher because we want to be pretty sure of our conclusions. The most common confidence interval is 95%. Let us interpret our confidence levels and confidence intervals. The confidence level is the overall capture rate for the population parameter if this method is used over and over and many times. Starting with the population, imagine taking many SRSs of 16 observations. The sample mean will vary from sample to sample,
It's 9
right?
o'clock.
But when we use the method of estimate plus or minus margin of error to get an interval, 95% of these intervals will capture the unknown population parameter mu. So here's what we have. We have our population. We're sampling a whole bunch of size 16 simple random samples. And we get a whole bunch of these confidence intervals. 95% of these intervals capture our unknown mean value mu. If we look at it this way, we have this normal distribution. We have this sampling distribution of x bar. These confidence intervals that we get, these red dots represent all of the point estimates. And the whiskers represent our confidence interval. 95% of these intervals will contain the true value of mu. Notice there's this one that does not contain mu. The rest of them do. That's what confidence level means. And each one of these is a separate confidence interval. The confidence level, to say that we are 95% confident, is shorthand for 95% of all possible samples of a given size from this population will result in an interval that captures the unknown parameter. That's a mouthful, lots of language. The thing you need to really get to know and get used to are these two statements right here. The one in quotations for confidence level, understanding what that means, and they're going to be worded virtually identical all the time. And the confidence interval, we say that we have a C% confidence interval. That C% is our confidence level. We are saying we are C% confident that the interval from something to something captures the actual value of the mean value of the amount of money we spend at Chipotle every month, or some other population parameter used in context in the problem. These two statements in quotations are very repetitive and worded almost identical from problem to problem. You just have to plug in the numbers, the C and the maximum and minimum, and say what the population is in the particular problem you have. The confidence level tells us how likely it is that the method we're using will produce an interval that captures the population parameter if we use it many times. There's that thing again. Long run behavior, ladies and gentlemen. This is not short run behavior. The confidence level does not tell us the chance that a particular confidence interval captures the population parameter. Not short run, it's long run, guys. The confidence interval gives us a set of plausible values for that parameter. We interpret confidence levels and confidence intervals in much the same way we're estimating the population mean, proportion, or some other parameter. All the same skills that we've been seeing get used over and over and over throughout this chapter.